This video contains examples involving video games and aggression. There is an example about alcohol affecting perceptions of facial attractiveness. None of this compares to the meditating spaniel saying the word butthole.
Hello. Now, unbelievably, this is about the 6th time that I've started recording this lecture, but you'll never know that because I'm going to edit out the other 5. Except you will know it because I've just told you. Anyway, this is another fun installment of things you can do with the general linear model. And the fun thing we're going to do with the general linear model today is look at how to analyze factorial designs. Now, we've seen this slide a lot of times, and it just reminds us that all the stuff we're learning about on this module is to do with how the general linear model, a statistical model, fits into a broader framework of analyzing data and addressing scientific questions. So as with the previous few lectures, we are just focusing today on this middle part of that process. So basically looking at how factorial designs fit within a general linear model framework. Now, of course, we're also going to talk about assumptions and robust variance as well, but fundamentally, we're just looking at how factorial designs fit with the general linear model. So hopefully, by the end of this session, you'll have an idea what a factorial design is, have an idea of how you would analyze them with a GLM and check assumptions and fit robust variance and all the rest of it. We're going to spend a bit of time talking about moderation and interaction effects because they are a key part of factorial designs, and look at how to break down interactions both visually with plots and also with something called a simple effects analysis. So first off, we need to deal with some terminology, because factorial designs are typically employed in experimental settings, so when you're doing experimental research. And there's a few kind of ways in which terminology sometimes varies, which can be confusing if you're not on your toes. So because I teach everything in a general linear model framework, I typically refer to outcome variables as outcome variables because they are, the thing you're predicting. The outcome of the model, and I tend to refer to variables that are predicting the outcome as predictor variables. I mean, it makes sense, right, to call them those things. Now, in experimental scenarios, you will sometimes, or quite often in fact, hear predictor variables referred to as independent variables. And this is because in experimental scenarios, the predictor variables are often manipulated systematically. So the researcher is actually kind of adjusting what happens to participants in certain conditions, or somehow kind of manipulating the kind of levels of that variable. So these variables are kind of not predicted from other variables, and therefore they are seen to be kind of independent or not influenced by other variables. So sometimes predictors are called independent variables. The outcome variable is sometimes known as the dependent variable, especially in experimental context. And that's because this variable does depend upon the variables that it's being predicted from. So in an experiment, the idea is you manipulate the independent variable and look at the effect it has on the outcome or dependent variable. So just be aware that when you hear things referred to as independent variables, we're talking about predictors. When we hear things referred to as dependent variables, we're talking about outcomes. So that's the first bit of terminology out of the way. What is a factorial design in the first place? Well, a factorial design is where you have 2 or more predictor variables that have been manipulated. So it's typically applied to an experimental design, where rather than just having one predictor variable that the experimenter is manipulating, there'll be 2 or more. So factorial design is where we've got several predictors, normally categorical predictors. So people might have been assigned to experimental conditions representing different things. So the factorial refers to the fact that there's more than one predictor or factor. You'll sometimes hear designs referred to in a general sense as a kind of n-way design, where n is a number. Like you'll come across phrases like 2-way design and 3-way design. If you're really unfortunate, you might read papers that have a 4-way or a 5-way design, but they're basically uninterpretable. So what that refers to is the number of predictor variables or independent variables that the experimenter has manipulated. So a 2-way design, a 2-way factorial design, means that there are 2 independent variables that have been manipulated by the researcher. A 3-way factorial design, there are 3 independent variables. So you can name your design using this kind of terminology. Finally, you get different sort of flavors of factorial designs that depend on how participants have been allocated to different experimental conditions. So what we're going to be talking about today are independent designs. So this is where there are different entities in all of the various conditions of the experiment. So the levels of independent variables will be manipulated by randomly allocating participants to different conditions. In the next lecture, I think, we'll talk about repeated measures designs. So this is where the same entities take part in all experimental conditions. So you get kind of repeated information from the same entities or same participants. And then the week after that, or the lecture after that, we'll look at mixed designs, which, as the name suggests, is a mix of the two. So at least one of your independent variables will employ different entities across the different conditions, and at least one of your independent variables will employ the same participants across its different conditions. So we will come back to repeated measures and mixed designs if that doesn't make any sense to you. In terms of independent designs, all the designs we're talking about in this session are independent designs. So people are randomly allocated to a single experimental condition. So first of all, we're going to have a look at a concept called moderation and what it is. And the example we're going to use has to do with whether video games lead to aggression, which is kind of it's been a bit of a hot topic in recent years. The idea that playing violent video games might lead people to be more aggressive. So you want to address the basic question of whether there's a link between video game use and aggression. So your outcome measure, the thing you're interested in predicting, is aggressive behavior, which I've called aggress in this data set. And you're trying to predict that from video game use, to say how many hours per week someone plays video games. But you might also be interested in personality characteristics that might influence this relationship. For example, there's a personality characteristic known as having callous unemotional traits. And this is, well, some people believe it's a precursor to psychopathy, psychopathic behavior. It's basically characterized by having kind of a lack of empathy and a sort of callous use of other people for your own gain. But anyway, in particular, I think the lack of empathy in this personality characteristic makes it a good candidate to potentially influence aggressive behavior. Because if you're aggressive, maybe that's because you lack the kind of empathic characteristics to kind of see things from the other person's perspective. So that might make you more likely to be violent towards other people. I don't know, I'm basically making it up as I go along. Now, when we talk about moderation, this is the theoretical model that we're talking about. We're talking about there being a relationship between a predictor and an outcome. So a predictor predicts the outcome, and the moderator acts on that relationship. So the moderator kind of sits there and it has some influence over that relationship between a predictor and an outcome. That's what moderation is. We can have a look at this by actually looking at the this scenario of hours playing video games predicting aggression, and seeing how moderation would sort of play out in the real world potentially. So what we have here is a plot, and it is showing hours playing video games on the x-axis and aggression on the y-axis. And the dots are data points that, let's imagine, we've collected. These are fabricated data, just in case you're wondering. And what I've done here is I've split the data by whether people have callous unemotional traits or not. So if you imagine this was like a diagnostic category where you could diagnose some people as having callous unemotional traits and others as not, we've kind of split the data into two groups. So those who have these traits, those who don't have these traits. I mean, in all probability, the traits lie on a continuum, but anyway, let's pretend they don't. So we've got two groups here. We've got a kind of callous unemotional group, and we've got a non-callous group. So what you can see, if we look at the non-callous group first, that's represented by this line at the bottom, and it's a pretty flat line, as you can see. So what that means is, as the number of hours playing video games increases, levels of aggression don't change. The line's pretty much completely flat. So what this is telling us is there's kind of almost a zero relationship between video gaming and aggression for those who have no callous unemotional traits. Now let's look at the group that has callous unemotional traits, and they represent, or the kind of summary of their data is the line at the top, which is sloping upwards. So what this tells us, the fact the line is sloping upwards, is as the number of hours playing video games increases, levels of aggression increase too. So for those who have callous unemotional traits, there's a positive relationship here between playing video games and aggressive behaviour. And this is what we mean by moderation. We mean precisely what's going on in this graph, that the effect of playing video games on aggression is different in one of the groups than it is in the other group. And in this case, for those with callous unemotional traits, there's a positive relationship. Playing more video games leads to more aggression, whereas those without callous unemotional traits, that relationship just isn't there. The more you play video games, it has basically no effect on your aggressive levels. So this is a kind of idealized illustration of moderation when you've got a sort of categorical moderator variable. What you're saying is the effect of one variable on the outcome is different across different categories of the moderator. Imagine now that we've measured callous unemotional traits on a continuum. So what we're looking at here now is how the relationship between video gaming and aggression plays out at different levels of callous unemotional traits on that continuum. So as we sort of move through the continuum of callous unemotional traits, how does the relationship between video gaming and aggression change? And these three-dimensional plots, which are probably a little bit hard to unpick in a way, kind of illustrate what we're looking at here. So we've got video gaming along the x-axis, we've got predicted aggression along the y. And callous unemotional traits is represented by this kind of z dimension of or z-axis, if you like. So what we can do is we can start at low levels of callous unemotional traits. So we'll start at the kind of left-hand side of this kind of z-axis. So those low levels of callous unemotional traits, so at this kind of point here, what's the relationship between video gaming and predicted aggression? And we can see it's kind of slightly positive. So there's a slightly positive relationship between video gaming and predicted aggression at low levels of callous unemotional traits. As we move up to kind of average levels of callous unemotional traits, we then can look at that relationship again. So is it different to how it was at low levels, or is it kind of the same? And hopefully you can see it's kind of the same. So again, if we trace out the relationship between video gaming and aggression at kind of average levels of callous unemotional traits, it's pretty much the same as it was at low levels. And at high levels of callous unemotional traits, we can do the same thing. And again, if we then track what the relationship between video gaming and aggression is at high levels of callous unemotional traits, again, it hasn't changed pretty much. This will be an example of no moderation. So this is where callous unemotional traits does not moderate the relationship between video gaming and aggression. So in other words, the relationship between video gaming and aggression does not change as you move along the kind of continuum for callous unemotional traits. Now, let's look at this other side. What's going on here? Well, what we've got here is an example of moderation. So when we have moderation, this relationship, the sort of core relationship we're interested in between video gaming and predicted aggression, does change as a function of callous unemotional traits. So in this example, if we start off at low levels of callous unemotional traits, what's the relationship between video gaming and aggression? It's actually slightly negative. So at low levels of callous unemotional traits, the more video games you play, your aggression levels get lower or are lower. So it's kind of a negative relationship. These are not real data. So let's move up the continuum of callous unemotional traits and see what happens at sort of more or less average levels. So at average levels, if we trace that relationship between gaming and aggression, it's become pretty flat. So it's gone from at low levels of callous traits being a negative relationship to at kind of average levels of callous traits. It's now pretty flat. There sort of is no relationship. Let's move up the continuum again to high levels of callous unemotional traits, and at high levels, I can't draw the line. Again, if we trace out this relationship, it has become positive. So the relationship between video gaming and aggression is different at different levels of callous unemotional traits. At high levels, it's a positive relationship. More you game, more aggression you show. At low levels of callous unemotional traits, it's negative. The more you game, the less aggression you show. So this will be an example of moderation or an interaction between video gaming and callous traits. So hopefully that gives you a kind of flavor of what we're talking about when we talk about moderation. Now, in terms of the statistical model we're fitting to test moderation, what we're basically doing, we're fitting a linear model, we're putting in our predictor variable, we're putting in our moderator variable, which is just another predictor, but we're calling it a moderator. And we also put in what's known as an interaction term. So the interaction between the predictor and the moderator. And all this interaction term is quite literally the predictor and the moderator multiplied together, which you don't have to manually do that multiplication. You can get your statistical software to kind of do it automatically for you, but that's essentially the model we're fitting: predictor, moderator, and their interaction, their combined effect. So in terms of what the linear model would look like in this particular example to do with video gaming, we'd be predicting aggression from, obviously we'd have an intercept, beta 0. We'd have the amount of video games played, or the hours playing video games per week, and that would have a beta attached to it, a parameter attached to it. We'd have the measure of callous unemotional traits with a beta attached to it. We'd also have this interaction term. We'd have the video game variable multiplied by the callous unemotional trait variable. And again, that would have its own parameter, its own beta. So we've got 3 predictors in the model: predictor, moderator, and their interaction. So as I said, the interaction term is literally the product of the 2 variables within the interaction. So if you're looking at the interaction of video gaming and callous unemotional traits, you're looking at the scores for hours playing video games multiplied by the scores for callous unemotional traits. And like I said, your software will kind of automatically create that variable for you, but that is, when you see an interaction term, that's kind of literally what you're looking at: two predictors multiplied by each other, included as another predictor. So when you look at this interaction term within your model, you can interpret it in kind of the usual way. So if it's significant, if you're into significance tests, if the interaction term is significant, then you have a significant moderation effect. So callous unemotional traits significantly moderates the effect of video gaming on aggression. The parameter estimate for that interaction effect quantifies the size of that effect. These are a little bit, that's a bit of an understatement, these are trickier to interpret, but as I will show you, the betas, again, are literally a raw effect size for the interaction. The effect of one predictor is stronger at some levels of the other predictor. That's what an interaction means, or moderation means. So in our case, if we got a significant moderation effect, it will mean that the effect of video gaming on aggression is stronger at some levels of callous unemotional traits than others. And in Factorial Designs, we're normally dealing with categorical variables, so categorical predictors. So what we're in effect saying is the effect of one predictor is stronger in certain categories of the other predictor. And we can pick this apart with a simple effects analysis. We're going to go through a couple of examples, so hopefully this will all become a bit clearer.
Hello, and welcome to Meditation with Milton. In today's lesson, we're going to learn the art of breathing to help you through those anxious moments, like when you're learning statistics. Now find a nice comfortable chair and relax. Focus on the breath. Focus on the breath. Remember, by focusing on the breath, you will not be distracted. Your mind can stay focused and at one with your body, undistracted by, oh, is that a squirrel over there? That's a squirrel. I saw a squirrel. There's definitely a squirrel over there. Oh, I love squirrels. Milton loves squirrels. I like chasing squirrels. I like chasing mine. Sorry, yeah. Relax. Focus on the breath. Don't allow your mind to wander. Oh, there's a dog. Dog. I love dogs. Dog. Where do you want to see the dog? Dog. Oh, I've completely forgotten what I was I doing something? I saw a dog. I don't remember what I was doing.
So let's look at our first example, and this is another video game related example. So imagine someone was interested in looking at whether playing games consoles led to injuries. So they measure injury severity during the play of video games, and this is on a scale fabricated in my own mind that varies from 0 to 20. They had 40 participants, and they were randomly assigned to 4 different groups. And across those groups, 2 variables were manipulated. The first variable was the type of games console used, so whether they used an Xbox or a Nintendo Switch. And the second variable that was manipulated across those groups was whether the game they were playing was a static game, where you're just sort of doing that, or whether it was an active game, like where you're jumping around waving waving batons. Do you know what? I just don't play video games. I don't know anything about video games at all. I had to even Google whether the Xbox still existed before writing this example. But let's imagine that there might be a world where you have to like waggle your games controller around in a very active way, or jump up and down, or do something, I don't know, something that might lead to an injury. I basically don't know what I'm talking about. So anyway, they're the variables that have been manipulated in this world where video games are probably different to the actual world we live in. So the variables we've measured, we've got one predictor, console, whether they were playing an Xbox or a Switch game. And remember, different participants played the Xbox to the ones that played the Switch. And another predictor is the type of game, whether it's an active game or a static game. And the outcome is injury severity. So the model we want to fit is we're predicting injury severity from the type of game played, the type of console that the game was played on, and the interaction between the two. So the sort of combined effect of gaming and the console used. And that final interaction effect is going to test for moderation. So is the effect of game on injuries moderated by the type of console used, for example? So what we're doing here, we've looked at the general linear model lots of times. We've seen that basically we can look at the total variability in the outcome, in this case in injury severity, and we can dice that up into a model sum of squares, so the variability explained by the experimental manipulation, or in this case it's manipulations, because we've manipulated both console and the type of game. And there'll be another bit of variance, which is the kind of unexplained variance, so the sort of error in prediction when we fit our model. In a factorial design, we're sort of subdividing our model sum of squares into different components. So there'll be a sum of squares that's attached to the first predictor variable. So we'll have a chunk of that model sum of squares that's attributable to the type of console that people were playing. We'll have a second slice of that model sum of squares that's attributable to the second predictor variable, so the type of game that was being played. And we'll have a chunk of the model sum of squares that's attributable to the interaction between game and console. So this is just to illustrate that the sums of squares are sort of calculated in exactly the same way as the other general linear models we've talked about. So the total sum of squares gets partitioned into sort of variance explained by the model and the variance that the model can't explain. So, the error in prediction versus the variance in injury severity that can be predicted from the model. But the model sum of squares gets subdivided into the variance attributable to these 3 effects. We can fit the model in a couple of ways. Now remember from the lecture on looking at adjusted means, that when we're looking at F statistics and we have more than one predictor, we typically want to use type 3 sums of squares. So just bear that in mind. We're going to again look at type 3 sums of squares, and we got a couple of options in R. There's a sort of an easier option and a harder option. So I'm just going to kind of lay out the pros and cons. One option is to use the affix package, and there's a function, well, there's a few functions that do the same thing, but the one I particularly like is the AOV_4 function, which is easier to use than it is to say. I would say this is an easier option because it automatically sets up the contrasts for you that ensure that you get type 3 sums of squares. So basically you have to do less thinking using this function. It also has a really neat function called affect plot, which will plot you an interaction plot with really minimal effort. So that is pretty cool. But it comes at a price, which is that you can't look at the parameter estimates of the model. You can only look at the overall F statistics as far as I know. And you can't look at diagnostic plots from the model. You can't easily fit robust methods to the models either. So it's a good kind of workhorse function, which allows you to not have to think too hard. But that ease of use comes with some restrictions. The other alternative is to just use the LM function, which we've used throughout this module. It is trickier because you do have to think about setting up orthogonal contrasts before you fit the model. Because to get type 3 sums of squares, you have to have orthogonal contrasts on your predictor variables. Otherwise, basically, you don't get type 3 sums of squares. So you have to manually set contrasts, whereas they're automatically set in the affect package. But having exerted that extra effort in thinking about your contrast, and I mean really you should be thinking about what contrast you want to set and all the rest of it, you get the benefit of, you can look at parameter estimates for the model, you can look at diagnostic plots, and you can fit robust methods pretty easily. So it's a bit swings and roundabouts, so depending on how confident you are at R or indeed statistics, choose whichever one helps you to stave off the anxiety. As you can see from the little bits of example code I've got here, like there's a bit more code involved in using LM, mainly because, like I said, we have to set up the contrast before we can we have to set up some contrast manually before we can actually use LM. But anyway, those bits of code, they're all explained in the tutorial in the Discover package. So if you want to kind of play along at home in R, you'll get a lovely explanation in that online tutorial. It's not online, sorry, interactive tutorial. Okay. So overall, here is if we fitted this model. So what I do actually throughout is I give you examples of code if you're using the affect package and examples of code if you're using LM. And like I said, if you go through the Discover tutorial, you'll learn how to do both these things. I just want to highlight the fact that the model we're fitting, whichever one of these functions you use, we're predicting injury in both cases, and we're predicting it from game by console. And what the asterisk does in the R code is if you specify something like that, it will put in both the main effects and the interaction term. So although we've only written game times console, what's actually going into the model is the effect of game, the effect of console, and the interaction between game and console. It's like a shortcut for putting in sort of all standalone effects and the interaction effect. You can specify it in a more long-winded way, which again is explained in the tutorial if you want to go there. So we fit the model, and what we get out of the model is what's known as a main effect of game. So that's like the effect of game ignoring the effect of console and the interaction. The effect of console when we ignore the effect of game, and the interaction between game and console. Now, it's pretty important when you are looking at these sorts of designs and looking at interaction effects. If your interaction effect is significant, you can basically ignore the other effects. They're not interesting. Because, for example, if you find we do find a significant effect of the type of game, but given that we know that the effect of the type of game is also influenced by the type of console being played, that effect of game is not interesting because we know that it's influenced by the type of console that you use. So if your interaction is significant, the best advice is just to ignore all the other effects probably. Well, I don't know if it's the best advice, but it's advice at any rate. So what we see here is the effect of console overall is just about not significant. The effect of game overall is significant, but basically neither of these particularly matter because we have this significant interaction term. So this is telling us that the effect of game is influent on injury severity is influenced by the type of console being used. Right, let's dig into this a bit, into what these effects mean. So here's the data. Now notice at the bottom, so each dot, on this plot represent a participant's data. We've got injury severity on the y-axis, and we've got the 4 groups along the bottom. So Xbox players who had an active game, Switch players who had an active game, Xbox players who had a static game, Switch players who had a static game. So these are the raw data, and these are the means in each group. So the model we're fitting is effectively, as with all the other linear models we've looked at, when we've got groups or categorical variables as predictors, our predicted values are the means of the different groups. Now, when we look at what's known as the main effective console, so like the overall effective console, what is that actually looking at? So that's what we're going to look at now. Now, before we do this, what I'm going to do is I'm going to press a magic button that's going to it's going to switch this graph a little bit. So what I want to do is I want to get all the Xbox data on one side of the graph and all the Switch data on the other side of the graph. So, So notice at the moment, we've got Xbox and we've got Xbox. So we want those 2 bits of Xbox data to sort of be together. So with a magic button, just watch the screen, see what happens. Nothing. Watch what happens. Hey! So we've switched those 2 groups around. So we've just moved the data points to different locations. So now we've got the 2 Xbox groups side by side. We've got the 2 Switch groups side by side. And just to kind of make it really clear which people were playing the Xbox, which people were playing the Switch, I'm going to invoke some magic colors as well. So now all the Xbox data points are in the same color and all the Switch data points are in the same color. And we've basically got all the Switch data points over here, all the Xbox data points on the left over there. So when we look at the main effective console, what we're effectively doing is just lumping all of these data points together. So we're just saying anyone that played the Xbox, we don't care what kind of game they had, we'll lump all their data together, we'll calculate the mean. We'll do the same for the Switch condition, we'll just lump all the Switch users together, take the average of all of their injuries. What do we get? And the main effective console is testing that difference there. So it's saying, is that mean different from that mean there? So it's just looking at that kind of difference there. So it's lumping all the Xboxes together, all the Switch people together. If we look at the main effective game, well, what we're asking here is whether the active games lead to more injuries than the static games, or vice versa. So again, what I'm going to do is I'm going to put all of the active game data in the same color and all the static game data in the same color. So now anyone who played an active game is on the left hand side of the screen, anyone who played a static game is on the right hand side of the screen. And again, having lumped all those data points together, we could calculate the mean. And if we do that, we get these 2 values here. So we get the mean number of injuries for active games and the mean number of injuries for static games. So again, the main effective game, so when we look at game in isolation, we are just comparing these 2 means. So we're asking basically, is that distance there significantly different from 0? The interaction term is looking at whether injury severity can be predicted from the 4 means kind of separated out, which is why it kind of doesn't make sense, because for the main effects we lump like all the Xbox data together and we lump all the Switch data together, and then we lump all the active data together and all the static data together. If you get a significant interaction effect, it doesn't make sense to look at those main effects. You'd only really be interested in looking at the breaking apart that interaction term. So here are the parameter estimates for the model that we've just fitted. And again, like I say, not really interested in the main effector game, not really interested in the main effector console. We want to focus on this interaction term because it was significant. And we get a parameter value of 3.8. Now, with other models that we've looked at, we've used that parameter estimate as a way of interpreting the kind of raw effect. So this 3.8 represents the raw effect of the interaction term. But what does that even mean? I mean, actually, what the hell does that mean? Well, let's have a look at what the hell that means, because it can be tricky, to say the least. So just remember that value, 3.8. So we are going to return to it. So first of all, let's consider the idea of the variable console moderating the effect of game. So what I've done here is plotted the 4 means across the different combinations of Xbox, Switch, static and active game. And on the left, we've got the Xbox, and the 2 dots represent static games and active, or the mean of the static games and the active games. And then on the right, we've got the Switch. So people who played the Switch, and the 2 dots represent the mean of the mean injuries for those playing static games and the mean injuries for those playing active games. And we can ask ourselves, within the Xbox, what is the effect of game? So what is the effect of game when you play the Xbox? And the effect of game is going to be the difference between those 2 dots. So it's the difference between 7 and 9.4. It's the difference of 2.4. So the effect of game, the effect of static versus active in the Xbox is 2.4. And the effect of game, so static versus active in the Switch, there's a bigger gap between the dots. It's actually a gap of 6.2. So 6.2 more injuries when you play active games in the Switch versus static games. So what's the effect of game when you play the Switch? Well, it's the mean of active games on the Switch minus the mean of static games on the Switch, which is a difference of 6.2, as shown on the diagram. What's the effect of game in the Xbox? That will be the mean of active games on the Xbox minus the mean of static games on the Xbox, which is a difference of 2.4, as shown on the diagram. So the interaction effect is the difference between these 2 values. So it's saying it's the difference between the effect of game when you're playing the Switch and the effect of game when you're playing the Xbox. It's 6.2 minus 2.4. That's where our 3.8 comes from. So it's kind of telling us the relative difference in the effect of game on the Switch compared to the Xbox. You can, though, also test this formally. So you can use something called a simple effects analysis, which does exactly this. It formally tests the effect of the type of game within each console separately. So what we see in the output here is the effect of game when the Xbox is used. And that effect is just about non-significant, although, you know, it's close. And this is the effect of game when the console is Switch, which is a bigger effect. It's a highly, highly, highly significant effect. So it seems like the effect of playing active versus static games is less significant for the Xbox than the Switch. So the difference in mean injuries between active and static games for the Xbox, and that difference was 2.4, is not significantly different from 0. Although, you know, like I said, that's inherently a slightly daft statement because the whole 0.05 cutoff is fairly arbitrary. The difference in the mean injuries between active and static games for the Nintendo Switch is significantly different from 0. So that difference of 6.2 is significantly bigger than 0. So what we've basically got is a much stronger effect of game when on the Switch than the Xbox. So active games versus static games, the level of injury that you get is that difference is bigger for the Switch than it is for the Xbox. You can also flip this around the other way and say, what's the effect of game moderating the effect of console? So how does the type of game moderate the effect of console? So I've replotted, they're exactly the same means. The values on this plot are the same as on the previous plot. But what's different is that I've now arranged the static means on the left and the active means on the right. And the coloured dots now represent Xbox versus Switch. So first of all, let's look at static games. So what is the effect of console when the game is static? And well, you can see the effect is basically 0 there because the dots are in sort of the same place. It's actually minus 0.30, so those means are practically identical. And what's the effect of what's the effect of console for active games? Well, here we're looking at the difference between injuries in the Xbox and the Switch, but only for active games, and there's a difference of 3.5. And again, just to sort of formalize this a bit, so we're saying what's the effect of console for active games? Well, it's the mean number of injuries for active games on the Switch minus the mean number of injuries for active games on the Xbox, and that difference is 3.5. What is the effect of console for static games? So here we're looking at the mean static games in the Switch and subtract from it the mean injuries for static games on the Xbox, which is a difference of minus 0.3. So the interaction is basically the difference between those two effects. So the difference between the effect of console in active games and the effect of console in static games. So it's 3.5 minus 0.3, which gives us 3.8 again. So that's where the parameter comes from. Again, we can formally test this with a simple effects analysis. So here we're just flipping how we're doing it. So now we're looking at the effect of console within each level of game. So you can see for static games, the effect of console is highly, highly non-significant. That you could see the two dots were practically in the same place. There's virtually no effect there. But for active games, the effect of console is highly significant. So for active games, injuries were there were many more injuries, or the severity of injuries was much higher for Switch games than it was for Xbox games. So the effect of the type of console is less significant for static games than for active ones. So that effect of console only seems to kick in for active games. So we're saying the difference in mean injuries between the Xbox and Switch games that are static is not significantly different from 0. Whereas the difference in mean injuries between Xbox and Switch games that are active is significantly different from 0. And just to drum this point home, it is never sensible to interpret main effects in the presence of a significant interaction effect. So if you get a significant interaction, just focus on the significant interaction. Don't worry too much about the other effects. In terms of effect sizes, when you're using Factorial Designs, well, we've seen that we can use the actual parameter estimate as a raw effect size, but it is quite difficult to tease apart. But it's basically telling us that the difference in mean numbers of injuries when playing active games compared to static ones on the Switch is 3.8 injuries more than for the Xbox. I mean, you know, it's a mouthful, right? An alternative way to think about it is when playing the Switch compared to the Xbox, there were 3.8 more injuries for active games compared to static ones. So it's giving you this kind of relative effect. And bearing in mind 3.8 injuries on that 20-point scale, you know, it's a reasonable number of extra injuries. You can also get R to produce something called partial omega squared. So this gives you the effect of each predictor, or an effect size for each predictor. That's kind of the proportion of variance in the outcome that's not attributable to the other predictors. So in the case of the data here, our interaction effect, which is mainly what we're interested in, we get a partial omega squared of 0.09. You can times it by 100 to make it a percentage. It's basically telling us that interaction explains 9% of the variance in injury severity that's not attributable to the other predictors. Because this is a linear model, we can look at diagnostic plots in exactly the same way as we have with other linear models. So this shows us, for example, the residual plots at the top. Bearing in mind the lines here are supposed to be fairly flat. That's not too bad. That is quite flat. It's looking, so the plot on the right hand side on the top is more sensitive to heteroscedasticity than the one on the left. And that is looking a bit less flat than the one on the left, but it's not too bad. We can look at normality of residuals, even though that's not particularly important, but they do look pretty normal. All the dots here are hanging around that diagonal line pretty closely. And we could look at values of Cook's distance, see if there are any of those that are exceptionally big, and basically there aren't. They're all pretty small, none of them close to 1. So the model's looking like it might not be, like the assumptions are probably met. If they weren't, if you use LM, then you can fit robust models in the same way that we have when we've used LM before. So you can, for example, get heteroscedasticity consistent standard errors by just throwing your model into the model parameters function of the parameters package. And notice the parameter estimates themselves don't change, but the standard error does. So what's kind of robust here is the standard error, the confidence interval, and the significance test. So the interaction is still significant when we do a robust test, which is reassuring.
Welcome to Milton's Meditation Minute. Find yourself a comfy, relaxing chair and focus on the breath. Breathe in and breathe out. Breathe in, breathe out. Now, I often hear people say, you should be a bit more dog. And I agree. The secret to a happy life is the following. Wake up in the morning, sniff a butthole. Go down the road, sniff a butthole. Lunchtime, sniff some buttholes. Afternoon, sniff a butthole. Evening, sniff a butthole. After dinner, sniff some more buttholes. And then go to bed and dream about all the buttholes that you could have sniffed the following day. That's right, be a little bit more dog.
Let's move on to a second example. So this is an example based on a kind of social phenomenon, the beer goggles effect. So the beer goggles effect is the idea that your subjective perceptions of physical attractiveness become inaccurate after you drink alcohol. And this is a kind of weird example, possibly of science reflecting art, I'm not sure. But I had a fabricated example involving the beer goggles effect in an early edition of my textbook, and since that was published, people have actually started doing research on the beer goggles effect, which is amazing. I'm not saying that's down to me at all, but it is. It does amuse me. So there was a study in 2014 that was based on some actual science rather than my fabricated example. So alcohol consumption has been shown to reduce the accuracy in symmetry judgments. So if you've drunk alcohol, you're less good at judging symmetry, and symmetrical faces have been shown to be judged as more attractive than asymmetrical faces. So their rationale was if the beer goggles effect is driven by alcohol impairing symmetry judgments, then you've got a kind of a mechanism in play then. So, you know, one of the reasons why your perceptions of attractiveness are affected by alcohol is because your symmetry judgments are impaired. So the data in this example are fictional, but they match the findings of the Chen et al. Study. So I couldn't get the actual data, but basically I've fabricated data that sort of mimics what they found. So in our fabricated example, we have just 48 participants, 8 per group. We've got one predictor variable, which is levels of alcohol. So one group were given a placebo, so they were given a 500 milliliter drink of alcohol-free beer. A low-dose group had 500 milliliters of beer that had a relatively average ABV, so not sort of averagely strong beer. And then a high-dose group had the same quantity of beer but a high ABV, so a relatively strong beer. So that's first predictor, which alcohol group they were in. The second predictor is the face type. So they had to rate 50 pictures of faces that were either basically asymmetric or symmetric, but we're going to refer to them as unattractive, the asymmetric ones, or attractive symmetric, because we know there's that relationship there between asymmetry and judgments of attractiveness. And the outcome, so they rated these 50 pictures, and the outcome is simply their median rating of these 50 pictures. So on a 10-point scale, they had to rate each picture on pass me a paper, 0, it's like pass me a paper bag, 10 is pass me their phone number. In case that's not clear, 10 is a good rating. 10 means you think the person is attractive. So they rate 50 faces, we take their median rating. So this is an independent design. So a given participant was only in one of the 3 alcohol groups, and they either rated 50 attractive faces or they rated 50 unattractive faces. They didn't mix it up at all. So here's what the data show, and effectively you can see we've got the doses of alcohol on the bottom in order: placebo, low dose and high dose. And it looks like for the asymmetric or unattractive pictures, in the placebo the ratings are low, but as alcohol consumption increases, those ratings go up. For the symmetric faces, the attractive faces, the dose of alcohol doesn't seem to have too much of an effect. So the ratings don't really change that much across the alcohol groups. But let's see what the analysis actually shows. So here's the model fitted to the data. There's the R code if you want to, like I say, play along in R. That's also this is also in the tutorial. And first off, well, we do get a significant interaction effect. So whatever effect alcohol has on ratings of attractiveness, it is moderated by the type of face that's being rated. Or you can flip that around and say, whatever the effect is on rating symmetric versus asymmetric faces, that effect is different at different doses of alcohol, because you've got a highly significant interaction effect. So we could look at the simple effect of face type within alcohol group to break that interaction down. So in the placebo group, the effect of face type is highly significant. So it looks like certain types of faces were rated significantly higher than other types of faces in the placebo group. And if you look back to the graph, it's actually that the attractive faces are rated significantly higher than the unattractive or asymmetric faces. So in the placebo group, you get the symmetry effect that you would expect, basically. Symmetric faces are rated higher than asymmetric ones. What about in the low dose group? In the low dose group, the effect of face type is still significant. So it looks like even with a low dose of alcohol, so 500 milliliters of average strength beer, we're still seeing this effect of symmetric faces rated as more attractive than asymmetric ones. But as we move into the high dose group, so those who had a strong drink of beer, that effect disappears. So at high doses of alcohol, the attractive and unattractive faces were not rated significantly differently by the participants. So it's basically showing the beer goggles effect. So at low doses of alcohol and no doses of alcohol, there is a difference in that symmetric faces are rated as more attractive than asymmetric faces, but that effect is kind of wiped out at high levels of alcohol. So it looks like, you know, as the alcohol kicks in, your judgment is indeed impaired. So what the simple effects are showing us, just to recap, is that in the placebo group, the difference between ratings of unattractive and attractive faces are significantly different. They're also significantly different in the low dose group, but they are not significantly different in the high dose group. If you do the simple effects the other way round, you wouldn't necessarily do it both ways round, incidentally. You normally would just pick the way that makes most sense for your hypothesis, which in this case is possibly the way that we've just done. But you can look at the effect of alcohol within face type. So for the unattractive or asymmetric faces, the effect of alcohol is highly significant. So when you're rating asymmetric faces, your ratings are influenced by how much alcohol you've had. But when you're rating attractive faces or symmetric faces, the effect of alcohol is not significant. So alcohol only has an influence on the judgments of asymmetric or unattractive faces. Recapping that with our plot, what we are effectively saying is that this change in means for the unattractive faces is significant, but the change in means for the attractive faces are not significantly different. Again, we can look at diagnostic plots, and the basic message here is, if we look at our residual plots, we've got a lovely flat line there, which looks like there's no problem with heteroscedasticity. on the plot up here, which is more sensitive to heteroscedasticity, it's still looking reasonably flat. It's flat enough. Again, our residuals look fairly normally distributed. All these dots are clustering quite closely around the line. Our Cook's distances are all well below 1, so it basically looks like a fairly unproblematic model. So just to summarize, Factorial Designs is where 2 or more predictor variables are manipulated by the experimenter. Moderation is where the effect of one predictor differs at levels of another predictor. Testing moderation, we do that with looking at interaction effects. So the model is a linear model in which predictors are entered as well as their interaction, their combined effect. We interpret interactions using plots or simple effects analysis, or indeed attempt to interpret the parameter, if you're brave. What these will do is quantify the effect of one predictor at each level of the other. We can test model assumptions in the usual way with diagnostic plots because we're just fitting a linear model, so nothing's changed there, and we can fit robust variance if we need to in the same way because we're just fitting a linear model. And just a word on main effects again. If the interaction is not significant, you would be interested in the main effects, so it's worth at least having an awareness of what they represent. So the main effects show the effect of one predictor collapsing across levels of the other predictor. So in the presence of a significant interaction, they're not interesting, probably not worth interpreting. If the overall interaction effect is not significant, then you might want to interpret the main effects. But typically, if you have an interaction effect, it's because that effect represents your kind of central hypothesis. So it may be the case that even if your interaction is not significant, you are just not interested in the main effects. Okay. That's it. Thanks for listening, and I will be back soon. Bye.